Next, we will introduce more details of this example. Let's have a closer look at the input and the output. In fact, almost all big data computing components use word count as their test code. The input is a file containing 3 sentences. Hello world, by world. Hello Hadoop, by Hadoop. By Hadoop, hello Hadoop. The output is the result, showing the number of times the word appears in the input file. The word Hadoop appears 4 times, none in the first sentence and both 2 times in the second and third sentence respectively. We can check other words to prove the result is correct. Now we have the input and the output of the word count program. Let's look at the detailed process of map task and the reduce task. Here we have the for logic of mapreduce based on the word count application. Suppose we have a text document A, and if the user needs to analyze the time of each word repeated in A, the mapping process is as follows. Step 1. Divide file A into 3 sentences and launch 3 map tasks in parallel. Step 2. The word count program provides user-defined map functions. Here is a question. Why should there be 3 map tasks? Yes, exactly. Because the number of map tasks is determined by data segmentation. Now, file A is divided into 3 parts. So 3 map tasks are required. Step 3. The output of map task 1, 2, and 3 is an MOF file that has been partitioned and sorted but not combined. For details, please see the tables in the slide. MOF files record information in key value pairs. Here, we don't emphasize the uniqueness of each key, which means that every time we encounter a word, whether we see it or not, we always counter it once. Then input the MOF file into the reduce step. Now we have entered the reduce process, which includes the following steps. The results of each MOF files can be combined in advance. Specifically, it just adds the number of the same words together. In fact, combination helps to reduce the network transmission costs. In the phrase of first map output 12 messages need to be transmitted, while after the combination, only 9 messages are needed. We have reduced 25% network transmission cost through combination. It's an amazing operation, right? Then the MOF files need to be shuffled. Do you remember the meaning of shuffle? Shuffle is used to collect data with the same key on the same server, just as displayed in the graph. All of the hello scattered on different machines can be collected in one server. At this point, the key is the word hello and the value is the number of times on each machine. In preparation for the next operation, reduce. At this phrase, we need a user-defined reduce function. In the word count application, the reduce function just adds the count of same words together. And you may have found it very similar to what you did during the combining process. This is not a coincidence. And that's why we say a combine process is actually a small reduce step. And by the way, the combining step is optional, because it just preprocesses something that reduce will do. Now we get the number of each repeated words in files. Someone may think the example is too simple. How to use mapreduce in real business analysis? In fact, the processes are very similar, but functions are different. MapReduce only provides users the framework. We can apply it into various offline computing schemes. After introducing the architecture of MapReduce, let's have a look at Yarn. Yarn follows a typical master and slave structure shown here. The resource manager is a boss, and it's in charge of the resource management for the whole cluster. The node manager is like the department manager. They run on all nodes in the cluster to launch and monitor containers, and periodically report node status to resource manager. What is a container? You can regard it as an abstraction of the resources provided by Yarn. It mainly contains memory and CPU resources which can be used. There is another container, the application master. The application master is like a team leader, responsible for coordinating resources from the resource manager, performing and monitoring component tasks with node manager. A container is a set of computing resources that can calculate all task instances. The container uses resource constraint sets, including memory and CPU, to execute application-specific processes, and reports the status of mapreduce tasks to application master. Please remember that an app master is a special container, but it has more responsibilities. When the job starts, the application master calculates the required resources and then applies for them from the resource manager. It's also the application master that informs the resource manager to call back resources after the task is completed. In this figure, two clients submit tasks to Yarn. The blue line indicates one task process, and the brown line indicates another task process. The resource manager receives the task submitted by the client, starts and monitors the first container, app masters. App master notifies the node manager to manage resources and start other containers, and the tasks are running in containers. Now, let's see more details about the task scheduling process of mapreduce on Yarn. The client submits a job to resource manager. 2. The resource manager receives the job and allocates the first container for the application program and asks node manager to start application master in container. 3. The application master registered with resource manager, so user can directly see the running status of the application. 4. After that, application master uses RPC, remote procedure call protocol, to apply for an obtained resource from the resource manager for each task, and monitors the task till completion. 5. Once obtaining the resources, application master asks node manager to start the tasks. 6. Then node manager starts the tasks. 7. Each task uses RPC to report its status and progress to application master, so that application master can restart the task if one fails. During the running of the application program, user can use RPC to obtain its running status from application master at any time. 8. After the application ends, application masters cancel its registration in the resource manager and close itself. This is the entire task scheduling of mapreduce on Yarn. Then we will learn the Yarn HA solution. Do you think it's familiar? Yes, we have talked about the high availability in HDFS. Resource manager in Yarn also uses an active standby architecture which ensures high availability. The high availability of resource manager is achieved by using an active and standby architecture. Similar to HDFS HA solution, resource manager HA solution allows only one resource manager node to stay active at a time. When the active resource manager node becomes 40, failover can be triggered automatically or manually to switch between active and standby states. In Yarn, application master may break down or shut down due to various reasons. Thankfully, Yarn has provided some countermeasures. If an application master goes down, resource manager will close all the containers that it manages, including containers where tasks are running. Then, resource manager will start a new application master on another computing node. But for services that run for a long period of Users don't want the entire platform stops because of the failure of an application master. Therefore, Yang supports the feature of preserving container status when starting a new application master, so that the tasks in these containers can run continuously without any failures.
In this part, we learned the mapreduce example in details, and even the basic principles of Yang. In the next section, we will learn the rules for resource management supported by Yang.